Yo, welcome back to Quantum Pinguino. Today we're going to be going into chapter 3 of Peskin and Schroeder and giving an introduction on Lorentz transformations in the context of the Klein-Gordon equation. So in the context of space-time coordinates, we can consider the Lorentz transformation as a 4x4 matrix lambda, which acts on the space-time coordinates, so this 4 vector that has 1 time and 3 spatial coordinates, as shown on the top. Not only do they transform our space-time coordinates, but they also change our inertial reference frame. Now, although the inertial reference frame has changed, it's important to note that the space-time interval, so this equation s squared, which represents the distance between space and time of 2 arbitrary points, remains invariant under Lorentz transformations, which means it remains the same. Just a quick note on notation. So I'm using the inverse Lorentz transformation with contravariant vectors for the rest of this video, just because this is the notation that was used in Peskin and Schroeder. But you might see them expressed differently, such as the forward Lorentz transformation with the contravariant vectors. It's okay as long as the indices are consistent and you keep your notation consistent throughout. But with this slide, I just wanted to highlight that in Klein-Gordon theory, the scalar fields have extrema that are mapped to corresponding extrema in the transformed reference frame under a Lorentz transformation. So what this equation is just showing is that if you have a field phi with some initial extrema x0 and you transform it under a Lorentz transformation to the new transformed field phi prime, then the extrema also gets transformed by the Lorentz transformation from x0 to lambda times x0. So now our goal is to show that the Klein-Gordon Lagrangian is itself invariant under a Lorentz transformation. So to show that the Lagrangian is invariant, we just need to show that the kinetic term and mass term both take on the same form after applying the Lorentz transformation. So we can do this trivially for the mass term, as it's just a function of phi, and we can just apply the transformation to the coordinates, as we did in the previous slide. The kinetic term is a bit trickier, and before we proceed in the derivation of its invariance, we need to derive 2 identities. So the first thing we have to do is find its identity for the derivative of the field as a function of the transformed coordinates. So the arguments of the field in both sides of the equation right now are literally the same thing. It's just on the left we omit the indices for clarity, but on the right we're going to show them as they're going to be useful when we start deriving. So we first start with a simple chain rule. We apply the derivative on the argument of the field, so the derivative of the inside, and then the right hand side is the derivative of the outside. So the term on the left simplifies quite nicely, as deriving with respect to x mu gets rid of the x mu on the top, and the term on the right just becomes the straight up derivative of the field itself. I do want to stress the difference between the derivative of the field and the derivative of the whole expression, because we don't have to apply product rule again. So otherwise we'd be stuck in an infinite loop. So this is exactly what we were looking for, just the chain rule of this derivative that we're going to use to directly plug in later. So with the next derivation, we're going to go back to the space-time interval that we briefly mentioned at the start of this video, and we're going to derive this expression that basically proves that the metric tensor is Lorentz invariant. So we start with the space-time interval, which itself is Lorentz invariant. We rewrite each of the x primes in terms of the Lorentz transformation of x, and then we just rearrange terms such that the Lorentz transformations are next to each other. So to match the form of the space-time interval given in the purple square, which is the untransformed one, we see that we have to require that this product between the metric tensor and the 2 Lorentz transformations has to itself equal another metric tensor with different indices. In English, what this is saying is that the metric tensor itself is invariant under Lorentz transformations. And it's also important to note that the Lorentz transformations act independently on each of the 2 indices of the metric tensor. So now we're ready to show that the kinetic term is Lorentz invariant. We start by expanding the squared and using the metric tensor to make both derivatives with lowered indices. This allows us to substitute in our earlier expressions for the derivative of the transformed field. We can go on a bit of a combo here and then use the second derivation of the Lorentz invariance of the metric tensor to rewrite the expressions in the blue boxes into a single metric tensor. We have successfully shown the Lorentz invariance of the kinetic term of the Klein-Gordon Lagrangian. To reiterate, we have shown this Lorentz invariance by showing that the Lorentz transform fields maintain the same functional form as the original fields with the spacetime coordinates appropriately transformed. So we've successfully shown that since both the kinetic and mass terms are Lorentz invariant, then the total Klein-Gordon Lagrangian is also Lorentz invariant. We have one more thing to do, which is to show that the Klein-Gordon equation is also Lorentz invariant. So this is going to feel like deja vu since they take on very similar forms. However, instead of having the partial derivative of the field quantity squared, as in the Klein-Gordon Lagrangian, you now just have a double derivative on a single field. Otherwise, it's literally exactly the same. You first apply the property of the derivative of the transformed scalar field, and then you also rearrange some terms and apply the Lorentz invariance of the metric tensor to simplify, and then you get our exact result again, which is that the Klein-Gordon equation is Lorentz invariant. So this basically covers the start of chapter 3, specifically page 36 in Peskin and Schroeder, and we'll continue on in chapter 3 in later videos. Thank you all for tuning in, and see you all in the next video.